So this is the video for total internal reflection lesson. Okay, so first things first, we always have to kind of acknowledge that on any given surface there's always going to be some reflection and some refraction. So hopefully, I think all of you have done the lab where you took the glass prism and you shone a light through, and then you saw the light bend either away or towards the normal depending on which medium was first. And here, hopefully you observe that always, or generally always, there's always like partial reflection and partial refraction. So if you can see the surface of this water, you can see the rocks that are underneath the surface, so that part's refraction because the light's traveling through the water. But you can also see the reflection of some rocks, reflection of the mountain, reflection of the trees, and their light is bouncing off the surface of water. So you can see kind of both going on at the same time. So let's look at this diagram and see what's going on. So again, so the first light source traveling along the normal and hitting the surface of the water. Some of it goes back, it's reflected. Some of it passes through without bending. And we learned that if the incident ray is along the normal, there's no change in direction. It just changes speed when it goes through the interface between medium. Now, this angle as an initial angle of some initial incident angle in water, and we can see that when air moves from a denser to a rarer medium, water to air, denser to rarer, it bends away from the normal. So my theta r would be greater, but there's also some part that's reflected, angle r, reflected angle, right? So both of those things are happening simultaneously. The key thing we're going to focus on here for total internal reflection, you can ignore all these things, is when you keep increasing your angle of incidence, your angle of refraction also keeps increasing until you reach this angle. So you can see here that this is the normal, this angle is theta I, right? What you would call your angle of incidence, and your angle of refraction turns out to be 90 degrees. So it's been completely away from the normal, and it's now basically towards or along the interface between the media. So we're going to define here critical angle. Critical angle is basically, it's an angle of incidence, right? That's the first thing. So critical angle is the angle of incidence for which the angle of refraction is 90 degrees. So what is critical angle? It is an angle of incidence. That's the first thing that you have to be okay with there. So when I say critical angle, I mean theta I, or angle of incidence, right? It's the angle of incidence when theta r equals 90 degrees. That's how the critical angle is defined. Now, why is it called a critical angle? Because any angle, any incident angle greater than the critical angle will not refract, because there's nowhere to refract to now, right? Because above 90 would just be over here, and that's not really refraction, that's reflection. So here you have what is called total internal reflection, where 100% reflection of incident light from a surface occurs because there's no refraction. All the refraction is being converted almost into reflection, because if there was to be refraction, it would bend away from the normal, and you can't bend more away from the normal than 90 degrees without going into or going back to the same medium. And so when it reflects from a medium, it follows the law of reflection. So angle of incidence equals angles of reflection. And therefore the reflected ray that was always there and the refracted ray kind of combine to form just a totally internally reflected ray. So again, the Fresnel equations are used to calculate how much of light is reflected and how much of it is refracted from a medium. We will obviously not be doing the Fresnel equations. I just wanted to show you that things are slightly complicated here. But there's two conditions for total internal reflection. One, light must be moving from a denser to a rarer medium. So again, for total internal reflection, you kind of get the idea that light has to keep moving away and away from the normal so that it can totally internally reflect at some point. If light moves from rarer to denser, it's bending towards the normal and will never actually reach the 90 degrees or be able to reflect because it's going towards the normal. So that is the first condition. The second condition is that the angle of incidence must be greater than the critical angle. So for any given angle of incidence, there is again some refraction, some reflection, but for an angle of incidence that's greater than the so defined critical angle, which has to be experimentally calculated or given to you in some way, if the angle of incidence is greater than that, that means the angle of refraction is greater than 90, which means it's reflected. So hopefully we are good with these two conditions for total internal reflection. So here, this is an important application of total internal reflection. And it has to do with a fiber optic cable. So here the fiber optic cable is basically a long cable made of glass or special kinds of plastic that transport or carry light at very high speeds from place to place. So basically internet and all computers that use like binary still use fiber optic cable, because light travels super fast and then you can transfer messages really quickly from spot to spot. So the fiber optic cable is made out of two substances. It's made of its core and something called the cladding. So light would be going through the core, hit the surface between the core and the cladding, and then be totally internally reflected here and here and here. So the cladding is made of a specific material, and then we have to say compare the refractive index of that to the core. So again, for total internal reflection to occur, it has to be going from a denser to a rarer medium, right? So the cladding should be made with a lower refractive index, or the cladding is rarer than the core. Only then the light will bounce off and keep getting totally internally reflected, because here's the cladding as well, right? And then it travels through the core like so. Okay, calculate the critical angle from water to air. Right, so here, again, we're using Snell's law. Ni sine theta I equals Nr sine theta R. So, again, for water to air, so in the incident medium is water, because you're going from a denser medium to a rarer medium. Right, so now, again, this is basically how all the questions are going to look like. The refractive index of water is 1.33. The refractive index of air is 1. We know this. Now, here's where we have to bring in our critical angle piece, or our total internally reflection piece, because here we define the critical angle as equal to the incident angle. So whenever I see sine theta I, I'm going to write sine theta C, because the critical angle equals the incident angle when the refracted angle equals 90. I'm sorry if I said reflected before. It's refracted angle equals 90 degrees. Right? So this is where I bring in my critical angle definition and my total internal reflection piece. So I'm going to rewrite this. So I'm going to write 1.33 sine theta C equals 1 times sine 90 degrees. So I'm just putting stuff into the formula. 1.33 times sine theta C equals 1 times sine 90. And here I have to calculate theta C. So again, I have both 1 and sine 90. I have values, so I'm going to calculate 1 times, or just put in, write 1 sine 90, which gives me 1. I'm going to move the 1.33 down to the denominator here. So I get sine theta C equals 1 over 1.33, which is 0.751879. Let's make that 8. And then I move the sine over to the front of the other side where it becomes sine inverse. So theta C equals sine inverse of 0.75188, which is equal to shift sine, and then you'll see in your calculator the sine inverse, and then you put in 0.75188, and then you get 48.75 degrees. So any angles that are greater than 48.75 degrees, like 55 degrees or 48.80 degrees, will be totally internally reflected when they pass through water to air. Any angles that are lesser than 48.75 degrees, like 30 degrees or 45 degrees, will not be totally internally reflected. They'll bend away from the normal, but they won't be, there will be some reflection, but there'll also be some refraction. And here, at 48.75 degrees, the refracted ray will pass, become perpendicular to the normal, or go parallel to the interface between two media, between the water and the air. Right? So that's that diagram. Very badly drawn. Alright, so here's some practice. We can just try, again, one more. We're just going to do acrylic to water. It's hopefully you can see that it's not too, I should say, we're doing, all the questions are the same, right? So we've already kind of done like water and air or water and glass. You have to put this together in a way that it always goes from the denser to rare medium. I said water and glass. This is obviously going from glass to water. If you'll remember the mistake I made by putting it the other way. If you do go from a rare to a denser medium, you'll get an error in your calculator when you try to calculate the angle, because it's impossible for the critical angle to exist when you're going from from water to glass, from rarer to denser, right? Because it's bending towards the normal. So this is assumed to be from glass to water. We're going to just do acrylic to water. So we know incident medium is acrylic, refracted medium is water, acrylic is not on this little chart, unfortunately. Let's see if it's on some other, I should have it on some page somewhere. Acrylic is 1.49, there we go. I will give you the ones that you need. Water we know is 1.33, and again here we bring in our critical angle piece. My angle of incidence is equal to my critical angle when my angle of refraction is 90 degrees. So instead of theta I, I'm going to write theta C. Instead of theta R, I'm going to put 90 degrees in. So 1.49 sine theta c equals 1.33 sine 90, or theta r, right? So I'm going to calculate 1.33 sine 90, which just turns out to be 1.33. Sine 90 is equal to 1. Move the 1.49 under here, so divide by 1.49. Sine theta c equals 1.33 divided by 1.49 is 0.8926. I've just moved this to the denominator, done the division, and then now I have to still get theta c, so I'm moving sine to the front over here where it becomes sine inverse of 0.8926. So I just put shift sine, or second function sine 0.8926, which gives me theta c equals 63.20 degrees. Right, so that is how you calculate the critical angle from acrylic to water. Same way glass to water is the exact same calculations, except Ni will be 1.52. Glass to air, Ni will be 1.52, and R would equal 1. This is part B. I've done part C here. Again, the same. Okay. That's the same piece right there. So you can kind of see where this is very similar. 1.52 sine theta c is equal to 1 times sine 90. 1 sine 90 equals 1. Bring the 1.52 down, divide by 1.52. I get sine theta c equals 0.6578. Move the sine to the front of the other guy, make it sine inverse. So sine inverse, which is shift sine, second function sine of 0.6578. Theta c equals 41.14 degrees. And so that's the critical angle. And you can hopefully do part A is the exact same as part C, except instead of 1.49 it's 1.52. So very little difference that's there. And that would conclude our lesson for TIR. Again, it's a bit longer than I'm hoping for, but there you go.